Hello, physics students, and welcome to this lesson about the properties of waves. This is an introductory lesson that will build on and probably review a lot of the concepts that you've learned in earlier science courses, like ninth grade physical science, for example. So I'm going to go over things briefly and then have a few checks along in this lesson for you to see how the understanding works for you. So basically what we're talking about a lot in the waves chapter is applying some of our terminology and then going to be using that when we talk about sound and light in future units. So some basic terminology we're going to be covering in this lesson. For the first thing, we want to define what a wave is. And in science, a wave has a specific term. We're going to be talking about a disturbance and how that disturbance is carrying energy. And so we're going to be taking a look at that. So in your notes, or if you want to make a list of terms, please use this idea of a wave being a disturbance that carries energy through matter and space. The medium is the term for the matter that wave is going through. So the sound waves that are using to make this recording are traveling through air. So air is the medium in that case. If it was a wave through water or maybe through a solid, that material would be the medium. So we have a few of those terms to keep in mind. Remember, waves carry energy, and they are going to be that disturbance, a repeating disturbance. A mechanical wave is a wave that needs a medium. So any type of mechanical wave, like the sound waves that I was talking about earlier, need a medium to travel through. Therefore, without the medium, there is no wave. And that's very true of sound. If you were to take the air out of this room, if we were in a vacuum somewhere, or if we were in deep space, there is no way for the sound to travel between the molecules of the medium, and therefore you wouldn't hear sound, even though somebody was trying to make that sound. So those are some things to kind of keep in mind. Mechanical waves need a medium, and the medium itself is what's traveling, and the disturbance moves through the medium. So it moves with the energy, but it's not traveling back and forth. So this leaf example is a really good one. So there's a leaf on the top of this water wave, and as the wave is moving from left to right, the leaf itself is floating on the surface, so it's moving up and down, but it's not being carried or pushed to the left or to the right, even though the disturbance, the wave, is traveling in that direction. So just some things to keep in mind. Vibrations and often cause waves, like my vocal cords are vibrating, or a musical instrument, the string or the reed would vibrate to make that that change in the medium. And a lot of waves are caused by this vibration. It is true for all of our mechanical waves, but there can be waves that aren't mechanical, and we call those non-mechanical waves. Light is a great example. And the object itself doesn't vibrate. So as a light is traveling through the medium, there are some fluctuations in the medium, but the main way for the wave to travel is actually the energy is vibrating. So it fluctuates in a repeating pattern, similar to the way the molecules in the medium might fluctuate as the wave transfers through energy through it. So we have to review a few terms just so we know we're all talking about the same thing. A transverse wave is a wave that we often think of. It's the wave that moves up and down like a string, or an ocean wave or water wave. It's that wave that's repeating that up and down pattern where the particles are vibrating up and down and the motion is moving left to right. We say that this is a perpendicular motion of the particles. So that the wave is moving to the right, the particles themselves are perpendicular to that motion. They're moving up and down in this example. Transverse starts with a T. If you flip that T around, you have the symbol for perpendicular. Easy way to remember it. So some examples might be ripples in a pond, earthquake waves, even light waves are transverse waves because their perpendicular energy is moving as the light wave is being projected. All right. The other type of wave, you might remember this from previous classes, is called a longitudinal wave. In that case, the particles move parallel to the wave. So a spring is a great example. As you compress or shrink a spring back and forth, the wave itself will move inside. So there's an area where it's tightly coiled and there's an area where it's loosely coiled. And that difference is what moves back and forth and carries the energy. So as the compression and refraction, it's called, moves through that wave and that spring, that's giving you the longitudinal wave through that. Sound waves are actually longitudinal, so they compress, and the air behind that compression expands to carry the energy through the air molecules or the solid molecules. And also earthquake waves. There are some earthquake waves that move as a compression wave through the ground. Those are parallel or longitudinal waves. All right, so we're going to come back to this idea, and I'm going to compare those two, transverse and longitudinal, and they both have similar parts of the wave. And this might also be a review a little bit, but we're going to talk about how to find these different identifying properties of a wave and parts. And we're first going to look at this transverse wave. So notice it has kind of that up and down or parallel motion if the wave is moving side to side this way. And we have a couple of things that we want to keep in track of. First is this dashed line that right down through the middle. We call that the equilibrium spot or the rest spot of the wave. Any distance above that is going to be the amplitude, or we could also measure from rest to a low spot in the wave. That's going to also be an amplitude. The next thing that we can measure is the distance between two identical parts of the wave. So in this case, we call them crests, where it's the top part of the wave, or two equilibrium spots, or two low parts, and we call those low parts troughs. Any of those distances between there is an identical measurement as long as this is a consistent wave, and that's going to give us the wavelength. We use this symbol lambda for wavelength, so you'll see that in your equations. And we can measure it with our SI units like meters and centimeters and so on. All right, so one thing that we're going to be practicing now is talking about how do we count the number of waves so that we can find things like wave speed down the road. If you look at these pictures, it's helpful to look at where the wave starts and where it comes back to that starting spot, because once it makes one full cycle, that is one wave. And then you can continue on. The reason this is 1.5, because it's making this full cycle plus another quarter and another quarter, that would add up to another half a wave. So this total is actually 1.5 waves. Because we're going from a trough on the starting and we're ending at a trough, that's one wave cycle. So that's one complete wave. Similarly, if we start on a crest and end on another crest, that is also one wave cycle. Now, the reason this is a half a wave is you can see here, if we were to project the rest of the wave, if we had it complete its full cycle, we would see kind of that mirror image underneath the equilibrium line. Half of that is just half a wave. This is also half a wave because it's having this quarter of the wave plus this quarter of the wave added together. And this one adds that, once again, the full wave is up to this point plus another half. So that's 1.5. I do want you to get pretty familiar with looking at these images, figuring out how many waves you have, and that's going to help us determine things like wave speed and other quantities as we're calculating those out. Okay, so I'm going to work with a few practice problems that's going to be using these ideas for you to construct your waves. They might give you some information about the amplitude and the wavelength. And then you're supposed to start at one part of the diagram and complete a wave that has those properties. So the reason this works, because the amplitude is 2 boxes, so I'm going up 1, 2, and notice that happens anywhere off of the equilibrium line. We're going up 2 boxes. And the wavelength needs to be 4. So if I count in the beginning, 1, 2, 3, 4, I end up at this spot right here. So I have a full wave, and I'm just going to repeat that process as I go along. If I want to count this, I have 1 wave here, 2, 3, and 4 total waves when I look at this picture. All right, so here's 1, here's 2, here's 3, and here's 4. Okay, so those are some things I'm going to have you guys practicing as well, and some of the practice in the homework. All right, here's just a slightly different variation where the amplitude is greater and the wavelength is also greater. So going from the start to the start of the next wave, we have 8 boxes. So that's our wavelength. And we're going up 1, 2, 3, 4. Okay, hopefully this is a review. I'm not going to spend a lot of time on this, but I do want you to be familiar with how to sketch out these waves given some information. Okay, lastly, we're going to talk a little bit about some of the calculations that go into it and how waves can carry energy. In fact, as you get farther from that equilibrium line, notice how this one has a greater spike, greater distance from the equilibrium. It's increasing the amplitude of that wave. It also means that that wave is carrying more energy. So if we think about this in terms of like a Wi-Fi signal, the signal would be carrying more energy would be a kind of a stronger, maybe more information is carried if it has that higher amplitude, so like turning up the volume a little bit on that signal. Lower amplitude means lower energy. Greater wavelength, though, means that you have less energy, and a higher wavelength means that you're carrying greater energy. Going back to that Wi-Fi example, you might be familiar with a 5.1 gigahertz or a 2.4 gigahertz kind of wireless network that you might have in your home. The reason that those things are different is they do carry their wavelength is what you're measuring, is comparing it to the frequencies. And what you're doing is you're actually carrying a different amount of energy. So you can carry different amounts of signal. You can carry more signal at the higher frequencies, the 5 gigahertz, than you can at the lower one, but it doesn't travel around objects as easily. The lower frequencies actually will bend around objects more, so you get a little bit better coverage. So those are some things we'll be talking about too when we talk about waves and energy down the way. So kind of connecting to that idea, I mentioned this already with my Wi-Fi example, but if you have a longer wavelength like this, it really means you have a lower frequency. What a frequency is how often the waves are occurring. Often we measure it in a unit called a hertz. So when we talk about a long wavelength, it's taking more time for that wave to get to that certain spot, so it's going to be less frequent. It doesn't happen as often. If you have a higher frequency, you're going to condense those waves. You're going to shorten and shrink them up, so your wavelengths actually decrease. And that means that you are carrying a little bit more energy at that higher frequency as well. You can think about clapping. If you were to do a slow clap, you're going at a lower frequency and your hands can be farther apart. So your wavelength might be the distance between your hands is bigger. If I try to speed that up, the only way I'm going to clap really fast is to bring my hands closer and closer together, and that decreases the wavelength. So higher frequency means shorter waves and shorter wavelength. All right, so we'll come back to a lot of those ideas as well. So how does this all fit together? We're going to be talking about this idea of a wave speed equation, where the speed of the wave traveling through a material. Now, this is different than the frequency. They're not the same thing, but it's actually how quickly the wave travels through its medium, if there is one, or how it just travels through space if there is no medium, is equal to the wavelength, so there's our lambda, times our frequency. And frequency is measured in a unit called a hertz, which is 1 over which is measured in 1 over seconds. Okay, so it's a special unit just for frequency. All right, so if we need to rearrange the equations, we sure can, but our unit for velocity will be a meter per second. So we're just like we have been in the past, we're going to be using that for our units. All right, so here's how these problems work out. You might have a piano that you know the frequency of 262 hertz. That's how fast the string is going back and forth. So every second it's going back and forth and vibrating 262 times. That's what that means. If their sound waves have a wavelength of 1.3 meters, what's the speed of sound in the air? So you can find that by just substituting in the wavelength, the 1.3 meters, times the frequency in hertz, 262 hertz. So we have about 340.6 meters per second. All right, so those are some of the problems that we'll do. Hopefully these problems are a bit of review. I'm not going to go through this one as much because it's just rearranging the equation. Remember, for scientific notation, if you're doing quest problems, you would write this as 3.0 e plus 8. So that times 10 to the power of is the e plus 8 notation in quest. And then you can solve for frequency. This one would be 6 times 10 to the 14th. If you're stuck on this, please pause the video, take a little bit of time, make sure you know how to do those rearranging questions. All right, so once again, just a quick review of kind of looking at different waves. The reason this is 1.5 waves is we start here, we go all the way back to the beginning, that's one wave, plus another half, okay? The period is 8 seconds. How do I know that? I'm using the graph down here because after one wave occurs in 8 seconds. The period is how long it takes for one wave. The frequency would be the reciprocal of that, or 1 over the period. In other words, 1 over 8 seconds gives me 0.125 hertz for the frequency. Amplitude, count your boxes. I get 3. And those are the types of questions I'm going to have you guys look at and answer. All right. So that kind of concludes that mini lesson on waves. I hope this helped you kind of get some big ideas about some of the wave, most of the wave terms that we're going to be using in this unit, and a little bit of the wave equation with wave speed. Thank you, and have a great rest of your day.